In this lecture video, we will take what we learned about rational expressions and learn how to solve rational equations. We will also finish this lesson by looking at an application problem. We'll start by solving this equation. 1 over x plus 2/3 equals 3/4. When we were simplifying complex fractions, we multiplied the numerator and denominator, or each term, by the least common denominator. Here, we will multiply both sides of the equation by the least common denominator. Looking at our three denominators, x, 3, and 4, the least common denominator needs to be a multiple of all three of these. So our least common denominator is 12x. Multiplying both sides of this equation by 12x, we have 12x times 1 over x plus 2 over 3 equals 12x times 3 over 4. Distributing, we have 12x times 1 over x plus 12x times 2 over 3 equals 12x times 3 over 4. Now let's simplify each term. Since we multiplied by the least common denominator, we expect that all three denominators will simplify to a factor of 1. Looking at our first term, 12x times 1 over x, our x's cancel out, leaving us with a factor of 1. With 12x times 2/3, we can simplify the 12 and the 3 as 4 over 1, since 3 goes into 12 4 times. And looking at 12x times 3 over 4, we can simplify the 12 and the 4 as 3 over 1, since 4 goes into 12 3 times. Now we have simply 12 times 1, or 12, plus 4x times 2, or 8x, equals 3x times 3, or 9x. This has become a simple linear equation, and we can solve for x. Subtracting 8x from both sides, we have that 12 is equal to x. It's important with rational equations that we always double-check our solutions. We need to make sure that no solution we come up with results in a 0 in any of the denominators. Looking back at the original equation, substituting 12 for x will not give us a 0 in the denominator. So we can say that this equation has a solution set containing the single value of 12. Let's take a look at example 2. In example 2, we have 9 over x minus 14 over x squared equals 1. Looking at our two denominators, x and x squared, we have a least common denominator of x squared. So we'll multiply both sides of this equation by x squared. We'll have x squared times 9 over x minus 14 over x squared equals x squared times 1. Distributing, we have x squared times 9 over x minus x squared times 14 over x squared. Simplifying, we expect to clear both of our denominators. With x squared times 9 over x, we can simplify one copy of x in the denominator with one copy of x in the numerator. And with x squared times 14 over x squared, we can simply cancel out x squared with x squared to become a factor of 1. So now our equation becomes x times 9, or 9x, minus 1 times 14, or minus 14, equals x squared times 1, or simply x squared. Now we have a quadratic equation to solve. We first want to write this in standard form. So we'll subtract 9x from both sides of the equation, and we'll add 14 to both sides of the equation. So we have 0 equals x squared minus 9x plus 14. The quadratic expression on the right can be factored as x minus 7 times x minus 2. And using our zero factor property, we know that this means that x minus 7 can equal 0, or x minus 2 can equal 0. If x minus 7 is equal to 0, then x is equal to positive 7. And if x minus 2 is equal to 0, then x is equal to positive 2. Now we double check our solutions for x. Substituting 7 for x in the original equation will not give us a 0 in either of the denominators. The same is true if we were to substitute 2 for x. So both of these solutions will work. We have a solution set containing the two values of 2 and 7. Let's take a look at example 3. In example 3, we will again start by looking for the least common denominator to help clear our fractions. We have two denominators, both of which are x minus 3. So the least common denominator is simply x minus 3. So we'll multiply both sides of this equation by x minus 3. Notice that this is equivalent to multiplying each term by x minus 3. And when we do that, we end up with x minus 3 times 2 plus x minus 3 times 7x plus 12 over x minus 3 equals x minus 3 times 4x plus 21 divided by x minus 3. Simplifying, we notice that both of our denominators of x minus 3 cancel out with our factor of x minus 3 in the numerator. This leaves us with x minus 3 times 2, or 2 times x minus 3, plus 7x plus 12 equals 4x plus 21. Distributing on the left, we have 2 times x, or 2x, plus 2 times negative 3, or negative 6. Combining like terms on the left, we can simplify this equation to 9x plus 6 equals 4x plus 21. Subtracting 4x from both sides and subtracting 6 from both sides, we have 5x equals 15, and we find that x is equal to positive 3. Now let's double check our answer. Substituting 3 for x back in the original equation will give us 3 minus 3 in both of these denominators, or 0 in the denominator. So in other words, the solution that we found of 3 is actually not a solution at all. In other words, this equation has no solutions. Now let's look at example 4. In example 4, we have two rational expressions set equal to one another. Let's start by factoring the denominators so that we can easily find a least common denominator. On the left, notice that x squared minus 8x minus 9 can be factored as x minus 9 times x plus 1. And on the right, notice that x squared minus 13x plus 36 can be factored as x minus 4 times x minus 9. Our least common denominator must include a factor of x minus 9, a factor of x plus 1, and a factor of x minus 4. So let's multiply both sides of this equation by this least common denominator. On the left side, notice that we can simplify our two factors of x minus 9 and our two factors of x plus 1. On the right side, we can simplify our two factors of x minus 4 and our two factors of x minus 9. This leaves us with x minus 4 times x plus 3 on the left and 6 times x plus 1 on the right. Distributing on the left side, we have x times x, or x squared, plus x times 3, or 3x, plus negative 4 times x, negative 4x, plus negative 4 times positive 3, or negative 12. And on the right, we have 6x plus 6. Combining like terms, we have x squared minus x minus 12 equals 6x plus 6. Collecting all of our terms on the left side will give us a quadratic equation in standard form. So we'll subtract 6x from both sides, and we'll subtract 6 from both sides. This gives us x squared minus 7x minus 18 equals 0. Now we have a quadratic that we can factor. This factors as x minus 9 times x plus 2. And using our zero factor property, we know that we can split this into two equations, that x minus 9 could equal 0, or that x plus 2 could equal 0. If x minus 9 is equal to 0, then x must be equal to positive 9. And if x plus 2 is equal to 0, then x must equal negative 2. Now let's double check our answers. Looking at our original equation, the denominator on the left side is equivalent to x minus 9 times x plus 1. And the denominator on the right side is equivalent to x minus 4 times x minus 9. If we were to substitute x equals 9, we would end up with a 0 in the denominator here and here. So x equal to 9 is not a solution. However, if we substitute negative 2 for x, we will not have a 0 in either denominator. So this equation has a single solution of negative 2. Let's go on to example 5. In example 5, we now have three rational expressions involved in our equation. Let's start by looking at the factored form for each of these denominators. X squared plus x minus 12 can be factored as x plus 4 times x minus 3. And x squared minus 2x minus 3 can be factored as x minus 3 times x plus 1. X squared plus 5x plus 4 can be factored as x plus 4 times x plus 1. Now we can determine what the least common denominator must be. It must include a factor of x plus 4, a factor of x minus 3, and a factor of x plus 1. Let's multiply each term by this least common denominator. Simplifying in each term, we find that we can clear all three of our fractions. That is, every factor in each denominator can be canceled out with a matching factor in the numerator. This leaves us with x plus 1 times x plus 3 minus 3 times x plus 4 equals x minus 3 times x plus 7. Now we need to distribute and collect like terms. Multiplying x plus 1 and x plus 3, we have x squared plus 4x plus 3. Multiplying negative 3 by x plus 4, we have negative 3x minus 12. And multiplying x minus 3 by x plus 7, we have x squared plus 4x minus 21. Combining like terms on the left, we have x squared plus x minus 9. Notice that subtracting x squared from both sides of the equation gets rid of the x squared term. Subtracting x from both sides of the equation gives us negative 9 is equal to 3x minus 21. Adding 21 to both sides of the equation, we have 12 equals 3x. And dividing both sides by 3, we find that x is equal to 4. Now let's double check our solution. Look at the original denominators. Substituting 4 for x in each of those factors will not produce a 0, so 4 is in fact a solution. This equation has one solution, positive 4. Let's look at a slightly different example. In example 6, we are asked to solve the literal equation for x. Recall that a literal equation is an equation containing two or more variables, and we can solve the equation for one of the variables by getting it by itself on one side of the equation. We want to solve for x, but right now x is in one of our denominators, and multiplying by the least common denominator will clear all three of these fractions for us. The least common denominator of y, x, and 3 is 3xy. So let's start by multiplying both sides of this equation by 3xy. And that's equivalent to multiplying each term by 3xy. So we have 3xy times 1 over y plus 3xy times 4 over x equals 3xy times 2 over 3. Simplifying, in our first term, we have a y in the numerator and in the denominator. Looking at the second term on the left side, we have an x in both the numerator and in the denominator. And on the right side of the equation, we have a 3 in both the numerator and in the denominator. So this equation becomes 3x times 1, or 3x, plus 3 times y times 4, or positive 12y, equals xy times 2, or 2xy. Recall that we are trying to isolate the x, so let's get both x terms on one side of the equation while moving the term with only y to the other side of the equation. We will subtract 2xy from both sides of the equation to have 3x minus 2xy plus 12y equals 0, and we'll subtract 12y from both sides of the equation to have 3x minus 2xy equals negative 12y. Notice that now we have only terms with an x in it on the left. So we can factor out an x. Factoring out an x gives us 3 minus 2y equals negative 12y. And dividing both sides of the equation by 3 minus 2y, we have found that we can express x as being equal to negative 12y over 3 minus 2y. As a side note, notice that this is equivalent to positive 12y divided by 2y minus 3. That's if we multiply the numerator and the denominator by negative 1, clearing that negative in the numerator. Now let's switch and look at an application example. In example 7, we are told that one hose can fill a pool in 20 hours, while another hose can fill the same pool in only 16 hours. The question is, how long does it take if we used both hoses to fill the pool at the same time? Consider the following relationship if both hoses are working at the same time. We'll have some portion of the job completed by hose number 1, and we'll have some portion of the job completed by hose number 2. And adding these two portions together gives us a total of 1, or a completed job. Let's start by looking at each hose separately. We are told how long it would take to complete the job with either hose separately. It takes 20 hours for hose number 1 to complete the job alone, and it takes hose number 2 16 hours to complete the job alone. This gives us the following work rates. If hose number 1 can do the entire job in 20 hours, then it can do 1/20th of the job in 1 hour. That's its portion of the job per hour that it can complete. If hose number 2 can complete the job in 16 hours, then it can get done 1/16th of the job in 1 hour. That's the portion of the job that that hose can complete per hour. The real question here is, how long does it take the two hoses to fill the pool together? Working together, we don't know how long this is going to take, so we don't know how long each hose is going to work. So we'll set our working time as a variable, t, but we can express the portion of the job completed by each hose in this amount of time. Hose number 1 is going to work 1/20th of the job per hour times t hours, or 1/20 times t. Hose number 2 will do 1/16th of the job per hour for t hours. So the portion of the job completed by hose number 2 will be 1/16 times t. Now we return to our original equation. The portion of the job completed by hose number 1 is 1/20 times t, or t/20. And the portion of the job completed by hose number 2 is 1/16th times t, or t/16. And in total, this adds up to 1 completed job. Now let's solve this equation for t. The least common denominator in this case is the least common multiple of 20 and 16, which is 80. Multiplying both sides of this equation by 80, we can simplify this to 4t plus 5t equals 80, or 9t equals 80. And dividing both sides by 9, we find that t is equal to 8 and 8/9 hours, or approximately 8.9 hours. That's the equivalent of 8 hours and 53 minutes. This is what we call a work rate problem. And that concludes this lecture video on how to solve rational equations. We also looked at an example of a work rate problem.